Okay, we will get started here. I do apologize I'm late. For those who haven't seen, McGill actually has a new machine learning little campus, a joint thing with University of Montreal, which is amazing, but it's not on campus, so sometimes traffic is a bit tricky. So today we're going to be talking about support vector machines, which are another type of supervised learning approach, a supervised classification approach that has one of the better names in machine learning, usually called SVMs. Now, before getting into that content, and I will say as a heads up, a fair warning, this lecture in comparison to the nearest neighbor instance-based lecture is a little heavy on the math side. So just be prepared for that, and I will say that my first time being introduced to SVMs, it took a little bit of kind of going over the lecture slides once or twice to get the details. So don't be really discouraged if at the very beginning it's quite a bit, especially compared to the very simple and intuitive nearest neighbor approaches. And there are a number of references provided on the schedule, in particular some links to not the usual textbooks, but some other background resources that can be useful. I will do what I can to give an intuitive description of these things, but that's just a bit of a fair warning about this lecture. So the other quick thing to mention is Mini Project 1 was graded. I'm sure most people are aware of that. So the average, I say, it's around 90. It's a little bit in flux as there's a couple regrade requests, things like that. In terms of common errors, so as I mentioned in an announcement about this, really for this mini project, only 10 points were for writing quality. And so most of the points were for kind of the correctness and the completeness. So the main places where people lost points was, first was having an incorrect gradient descent approach. And I want to just bring this up here because we've had a few people say, hey, I didn't know that my gradient descent was supposed to give the same answer as my closed form. That is something that is covered in the first lecture, or in the second lecture, where we talked about gradient descent. It's important to know that gradient descent will always converge to the same answer as a closed form approach. And so we didn't explicitly say that they had to have the same answer, but we said that your experiments had to match the trends in the reference solution and the kind of general mean squared errors. And so that's an unfortunate place where if you just run gradient descent and get a number, you might have, in some sense, a technical, like all of the code is correct, but it's really important that gradient descent should never give a different answer on a convex problem. So that's a place where points were lost. And then another place where points were lost is things like forgetting bias terms, so just bugs in code. So this assignment, we really emphasized correctness. So we weren't too harsh on writing quality. A lot of people lost a couple points for typos and clarity issues. Maybe up to 5 points if there were serious issues, or more than that if there was really serious issues. But I want to kind of emphasize here that when we're moving on to Mini Project 2, there is really no longer a big correctness component because your performance on the Kaggle competition, in some sense, is the proxy for that, for your performance of how well your method is doing. So in that sense, do well in the Kaggle competition, you will do well on that part of the assignment. But there's a lot more points for writing quality, and this time there were times we were taking off a couple points for typos, a couple points for really unclear figures, but we're going to move on to kind of a lot more grading focusing on the quality of the write-up report for Mini Project 2 and Mini Project 3, and then hopefully to give you lots of feedback in time for the longer project final report. So it's just a heads up that if you only lost a couple points on Mini Project 1 for writing quality, it was a small component of it, but it's important, I'm saying many times, to take your time writing a high-quality report, taking time to label your figures, write captions for your figures, have your axes labeled, have your figures be readable. So if the print is so small we have to zoom in a whole bunch, that is generally not a good thing, things like that. So that's the status of Mini Project 1. Like I said, overall the class did very well. An average of 90 is quite good, and that is because, again, here we're making sure everybody gets the very core linear regression implementations correct. Okay, so So that's on that. Are there any questions at this point about Mini Project 2 or any other logistical issues before we move on to the course content? Yeah. Great question. So the question was, mentioned in previous lectures, these sentiment lexicons and other resources. Are you allowed to use these sorts of external resources in Mini Project 2? Yes, you are, as long as you properly cite and explain how you use them. And as long as that does not involve looking at the test set or searching for the test set of this data set. So you're definitely allowed to use external sentiment lexicons. There's another question up there, or was it the same question? Okay, cool. Great question, yeah. Yes. So this is a good thing to reiterate that when you submit your results to Kaggle, it's being run on 30% of the actual test set. It's always the same fixed 30%. So if you're doing a kind of proper job in terms of doing lots of cross-validation and using that to choose your model, there shouldn't be a big difference between where you are in the leaderboard now and where you are in the leaderboard when we reveal the full test set. But you have to be careful if you're really just kind of tweaking things and seeing what gets you highest on the leaderboard and using up your 2 submissions every day just to see what little tweaks get you higher. There is a chance that some of the gains you're seeing will not translate to the final leaderboard. Again, it's probably only going to be a difference of definitely less than 1 percentage point in accuracy, but it's an important thing to remember that if you're really fighting, say, for that top 3 spot for those bonus points, it's much better to base your choices over what algorithms are working better on cross-validation rather than basing it on your submissions to the leaderboard. Submissions to the leaderboard should be the models where you're like, okay, I'm confident this is working. Again, that's why Kaggle does this held-out test set, to prevent people from hacking the full test set. Cool. All right, so with that, we will get started on the lecture for today. So returning to not linear classification, but classification in general. We remember when I first introduced the challenge of trying to classify data points into discrete categories, I mentioned these different high-level views of classification. So I talked about that these aren't necessarily kind of opposing or mutually exclusive views, but you can think about a lot of classification models in terms of probabilistic models or in terms of kind of decision boundaries. So you can think of your model as trying to figure out what is the probability of the class given the input, or you can think of the challenge really as being trying to specify some partitioning of the input space. And there's a number of models that can be interpreted in both of these ways, things like logistic regression, things like LDA and QDA. And now today we're going to be talking about a method that's kind of the quintessential decision boundary method. I mean, decision trees are as well. But this method we're going to talk about today, called support vector machines, really we're going to revisit the whole classification problem somewhat from first principles, really with the decision boundary version of things in mind. And just to give a quick outline, because this is going to be a bit of a two-parter, we're going to start this lecture on support vector machines today, and we'll continue on Thursday on support vector machines. So today we're going to talk about first what are called perceptrons. And this is kind of an interesting thing. We're going to go back to kind of first principles, really simple linear model for classification. And we're going to derive it in a slightly different way than we did for linear regression or logistic regression. And this simple model is going to motivate this idea of what we call margin and max margin classifiers, of which linear support vector machines are a very classic example, and we'll discuss those today. And then in the next lecture, we will discuss how to actually develop what can be called nonlinear support vector machines or kernel-based support vector machines. Okay, so starting off with this very simple model. So we're going to revisit the binary classification task. We're going to make one really minor modification to the notation, but it's kind of important for all the math and the rest of this lecture. So here we're going to assume that we have some set of input points. We have our features x, we have our outputs y. These are categorical outputs, just binary outputs in this case. But instead of having y be 0 or 1, y is going to be -1 or 1. This is a minor point, but it just is important for all the math and the rest of the lecture. So we're still just classifying things as true or false, but now false is -1 and true is 1. And the way that we're going to do this classification in the simplest possible decision boundary approach is we're going to just draw a linear threshold. So we're going to say our classification is going to be the sign function applied to our feature or our learn parameter vector times the feature weights. So this is just a simple linear threshold here, just like we had in logistic regression was linear, naive Bayes was linear, but in all those methods we're specifying this linear decision boundary and then interpreting this decision boundary in terms of the log odds and this probabilistic motivation. Here we're just saying there's a linear decision boundary, we draw on a line, and our decision is just a hard threshold function on this boundary. So the decision boundary is where the dot product of our parameter vector and our features is 0, and we're just doing a hard threshold on either side of this boundary. Yep. X and W to be. Yes, yes. In general, yes. And I do, so here I'm taking X and W to be column vectors. And I do apologize that occasionally there's inconsistency. Generally, things will be column vectors, but occasionally, for notational convenience, things will be written in different ways. We try our best to be consistent, but yes, they're column vectors in this case. Okay, so this is the basic simple classifier. It's a little bit weird that, again, we already talked about linear classification approaches, and we derive them in some really principled ways from Bayes' rule, and now we're just throwing all that aside and saying, okay, let's just have a linear classification boundary where it's just a hard classification based on a linear function. And how we're going to learn this thing, this is called the perceptron learning rule, and historically this goes back all the way to 1957, so this is really historically one of the very classic approaches to machine learning. And the rule here is quite simple. So how we actually train this perceptron is, what we're going to do is we're going to loop through all of our training examples. While there's some training examples that we're still making mistakes on, we're going to loop through the misclassified examples, and we're going to update our weight vector. It's just going to be an update where it's the weight vector equals the previous weight vector, a learning rate alpha, times the right output for this value, so it's either 1 or -1 times the features. So basically all this is saying is that if we should have classified this example as a 1, well then we're adding this term. If we should have classified this example as a -1, then we're subtracting this term. So all we're doing, it's similar to the gradient descent for logistic regression, say, that we've seen in the past, but here it's much simpler. We're just saying if you're supposed to say +1, we're subtracting the features from the parameter vector. If we're supposed to say -1, then we're subtracting, and +1 we're adding. Very, very simple idea, and in fact this was kind of derived without any formal intuitions about gradient descent or logistic or anything. This was just kind of from first principles, what is a reasonable learning rule. So, and in fact, you can interpret this in terms of gradient descent as a gradient descent on a particular error function. And this error function is a function where it's 0 if we classified things correctly. So if yi, so this is again always 1 or -1, if this times our decision boundary is greater than 0, then we made the correct classification. Because if this was supposed to be 1, if y is 1, then we want this to be positive, so this is all positive. If this was supposed to be negative, the target, then this is supposed to be negative, and a negative times a negative is a positive. So here we're saying we don't care how well we're doing on the positive examples, just as long, or on the ones we're correctly classifying, just as long as we're classifying correctly, there's 0 error. So it's different from this binary cross-entropy loss we talked about for logistic regression, which cared about the probability we were assigning. Here we're just saying, is it on the right side of the decision boundary? Good. If not, then our error is proportional to this term here. So again, for correctly classified examples, the error is just 0. And for incorrectly classified examples, the error tells us kind of how much we're misclassifying these examples by. And once we get down to 0, for this error function, then we're classifying the entire training set perfectly. Now, yep. This is a good question, yeah. If you were to run kind of the basic classic perceptron. So the question is here, for people listening on the lecture recording, when we say for all misclassified examples, every time that we update the parameter vector, do we have to loop over all training examples? Yes, in principle, that would be what you'd have to do, is you'd have to recheck if the update made you misclassify anything, and this algorithm will converge if the data is linearly separable, but in practice, nobody actually ever uses this really simple perceptron learning algorithm, but yes, that would be technically the correct thing to do. And actually, I think the easier way to think about it is just that you're doing gradient descent on this error here, and that will be equivalent to doing this whole for loop, because for any one where there's 0, you don't have to do any gradient descent update. So, but it's a great question. So, this approach is a reasonable thing to do, and it's actually going to work in kind of ways that we can guarantee as long as our data is linearly separable. And this is the concept we've mentioned somewhat informally, but here we're going to really focus in on this idea. And what this means is that if for all examples we have the correct classification, again, this term here is basically just saying, are we making the correct classification? If this is greater than 0 everywhere, then what this means is that our data set has a linear plane, so if we're looking in 2 dimensions, just a line, but in more generally a hyperplane, that can separate our data. And so some data sets are linearly separable, so you can look at this one here. But for example, this is a very simple, trivial example of something that is not linearly separable. So what's called this is actually, in logic, the XOR function is a very classic thing that is not linearly separable. But if we're focusing on data where it is nicely linearly separable, then there's what's called the perceptron convergence theorem. And what this says is that if the perceptron learning rule is applied to linearly separable data, then a solution will be found after a finite number of updates. So the issue is that if your data is not linearly separable, then this idea of making updates to your weights, checking which ones are misclassified, you might actually end up in an infinite loop. But if your data is truly linearly separable, then you will converge with this perceptron convergence theorem, telling us that we will find a way to separate the data. So, of course, the number of iterations we need for this is contingent on a number of things. For example, the learning rate we're using, the data set, etc. And if the data is not linearly separable, then we'll end up with an oscillation. So this will happen where, in some sense, we're going to update our weights. We're going to classify some points correctly, but now we're going to start misclassifying some other points that we were correct on before. And you can actually detect this. You can say, okay, I'm going back and forth. I'm doing these ones correctly, and now I'm doing these ones correctly. So it's possible to detect these things. Again, in practice, you're not going to use this basic learning approach. We're going to use an approach that we'll talk about towards the end of the lecture. And what you can do, just like with gradient descent, is that you can anneal, it's called, or kind of slowly decrease your learning rate. And even if the data is not linearly separable, you will settle on a reasonable solution. Again, if it's not linearly separable, this might not be the best solution, but you will settle on something if you slowly decrease your learning rate. So just what's a very simple example if we have a very nice data set? Looks like this. So we're trying to classify the blue points versus the red points. Say the blue points are positive 1 and the red points are class negative 1. If we apply this perceptron learning algorithm, we would get a line like this. And we would converge because this data is indeed linearly separable. Now, a neat thing to notice here, which seems like kind of just a funny point to make, but is actually going to become very relevant as this lecture goes on and as we move on to Thursday's lecture, is that we can actually represent the weights that we learn, the parameter vector that we learn, as a linear combination of our input data points. So recall that our learning rule is this very simple rule. We're just saying we're going to update our weights. They're going to be our old weights plus or minus, depending on what is the target here, the feature vector times the learning rate. And what this means is that if our initial weight started as 0, then at any step during the perceptron learning algorithm, our weights are going to be a linear combination of our input data points. Again, all we're doing to learn our weights is just adding and subtracting some constant times the input features for some data points. So this is the only change we're making, and what this means is that really at the end of the day, our learn parameter vector is going to be the sum over all of our data points, some alpha I here, so some weight for each of the data points, times the target for this data point, times the features for that data point. So at the end of the day, the features that we learn with this perceptron learning algorithm, these features are just some linear combination of all of our input. These parameters are just a linear combination of all of our input features. And I should note that due to conventions, the learning rate is called alpha, but these alpha i's here are a different alpha I. I apologize for that, but that is to be consistent with how the notation is done in the field. So another interesting thing to note here is that by the end of training, so for example, say there's some point that we've always been correctly classifying. At the beginning, it was good. We made all of our updates. Every time we were updating and we were changing our weights in our perceptron algorithm, this one point was always correctly classified. This would mean that we never actually had to use this data point in this update equation, and what that's going to mean is that that data point isn't actually used to compute our parameter vector. So what this means is that, in fact, our parameter vector that we learn using the perceptron learning algorithm is always just going to be some linear combination of our input features, but it might just be a subset of all of our data points. So only a small set of our data points might actually be involved in the learning. Again, because at the beginning, after we look at a few points, we might start correctly classifying most of the other points, and then we don't ever need to worry about those points. They're never involved in any updates. And we call this representation the dual representation of the classifier. And we call it the dual. It's related to duality in convex optimization. Again, things that will become more clear as this lecture goes on. And those of you who are very interested might want to read up into convex optimization. It's not going to be required for the midterm or anything, but it's called the dual, and this dual representation is basically the idea that there's one view of representing our classifier as this learn parameter vector, and there's one view of representing our learn classifier as a function of all our input points. And this is kind of interesting because in the last lecture we talked about these non-parametric or instance-based methods where we weren't learning anything, we were just storing our training data. Here there's kind of two ways to look at this classifier. One way we're looking at it where we're learning this parameter vector that summarizes our classifier. The other way of looking at it is we're just keeping around our training data and remembering how these training data points contribute to our classification boundary. So here I'm showing an example of, again, this same perceptron learning, what we learned in the end, and now the points that are bold are the points that were actually involved in the learning update. Now, one thing you might want to notice here is that this all seems... Oh, we got one question before we move on. Great question. So the question is, the ones that are bold, does this mean that these contributed to learning just in the last iteration or in any iteration? Technically in any iteration. And this is another point with this perceptron learning algorithm. And this is actually what brings us to the one of the main issues here is that, well, which points are bold here, which points are actually involved, is going to depend on the order that we do the updates in the perceptron learning algorithm. So if we remember, we had this learning rule, we're saying loop through all misclassified examples and perform this update. Well, this loop, depending what ordering we do for these data points, might change which data points are then involved in the update. So what this also means is that if you look at this plot here, you'll notice that this is a pretty reasonable looking line separating these two different classes. But There's a bunch of other lines. If we look at a data set like this, and for these examples that were involved, these bold examples, there's several different lines we could plot that would classify all of these correctly. So why did we choose the particular one? Why did we choose to pay attention to these particular data points? This is the issue, one of the issues with the perceptron approach, right? Is that, sure, it's always going to converge, but what it converges to is non-unique, and it depends on the ordering of the samples that we use in the updates. And that's not really a nice thing. So this method will converge to something, some reasonable decision boundary that can classify our training data if our data is linearly separable, but the exact specifics of that boundary are just determined by how we randomly ordered our data points. So that, for one, is a little unsettling. And it's also unsettling because, in principle, you'd think that, well, there's a right boundary to use. And that's what we'll come to in just a second. So another thing I'll just point out here is, getting back to this difference between this perceptron approach and this logistic regression approach that we focused on earlier, is one simple way to think about this is that for the perceptron, our decision boundaries is hard threshold, whereas when we were talking about logistic regression, we had this smooth function here. And so why is the perceptron somewhat of a nice algorithm, perhaps? Well, it's nice because it has this very simple kind of intuitive algorithm. We're just adding or subtracting the inputs features for points that we classify correctly or incorrectly. So that's nice. Downsides of it are that solutions are non-unique. They also can't deal with linearly separable data, and we don't have a nice probabilistic interpretation. Maybe something else that could be mentioned there is that in logistic regression, we had this way of interpreting our output as a probability of classifying something as a 1 or as a 0 or as a 1 or as a negative 1, where here we have no way of doing so. So now we're going to focus in on this non-uniqueness issue because this is really the biggest issue, and this is going to be the focus for most of the rest of the class. So again, if we consider a linearly separable data set, so for now we're going to presume that everything's linearly separable, the world's somewhat nice, but there's going to be an infinite number of hyperplanes that could separate linearly separable data, right? If we have class 1 and class 2, and there's some plane that can separate these things, we can always shift this by an infinitesimal amount. Unless we have an infinite number of data points, we can always shift this a tiny bit, which is unfortunate because it means it's non-unique, and it means that if I run my perceptron algorithm on my computer, and you run it on your computer, we can come to different things. We might have different performance on the test set, which is kind of weird, kind of unsettling. And really, we want to not just choose one of these planes. Really what we'd like to do is choose the best separating hyperplane. And a related question here is that we might not just care about classifying points, but obviously points that are closer to the decision boundary, those points are somehow we're more or less confident in. So we care about not just selecting some random plane, we want to get the best plane, and we somehow want the selection of this best plane to be related to how confident we are on the predictions we're making on the different data points. This is a great question. So the question was, given that the algorithm only actually converges when the data is linearly separable, isn't that somewhat a form of overfitting because we're going to perfectly classify the training set? Indeed. This is true, and in fact, the initial motivation for the perceptron algorithm back in 1957 was really not thinking about statistical generalization very much. It was really thinking more, how can we develop a simple computational learning rule that can learn interesting decisions. And the simplest thing you could think about is how can we have a simple learning rule that can separate data that obviously a human should be able to separate, just a linear decision boundary. So there wasn't really a big focus on statistical generalization when this was first derived, and indeed for almost the entirety of today we're going to be working in this world where we're talking about linearly separable data and how we can do the best on this linearly separable data. And in some sense, we're overfitting drastically to the training set in the entirety of this lecture. And then in the next lecture, we'll actually talk about the right way to regularize these approaches so that we trade off between coming up with good separating planes, but also having some tolerance for misclassified examples. It's a great question. So Now we're going to move on to what is called the linear support vector machine. It's called SVM. It'll become hopefully more clear why it's called an SVM as we get towards the end. But the key idea in an SVM is it's a perceptron. It's a simple idea. We're trying to learn a linear separating hyperplane. And the SVM is really just an algorithm that deals with this non-uniqueness issue. And what we're going to look at is we're going to look at something called the margin, which the margin is twice the Euclidean distance from the hyperplane to the nearest training example. So we're basically saying, what is the training example or setting of training examples that are closest to our decision boundary? What we want to do is we want to find the hyperplane that can maximize this margin. So instead of just saying, oh, we can use any separating hyperplane, we want the one that is separating the data the best. And by best is we're saying we want the width of this strip. So the boundary where there's no examples around our plane, this is called the margin here, we want this to be as big as possible. It's kind of like the no man's land, where around the decision boundary, once we're within the margin, there's no points in there. It's where it's in some sense almost like our confidence, right? If we have a really huge margin, that means we're separating our two classes by a huge degree. So we want this margin to be as big as possible. And this is a nice idea because this actually allows us to now come up with a unique solution, because there will be a unique solution that will maximize this margin. So suppose now that we have a decision boundary. So now we're going to think about how to actually compute this margin so that we can figure out how to maximize it. So suppose we have a decision boundary that separates the data. Shown here. Our decision boundary is going to be this line here, and our W vector is the normal to this decision boundary. Again, we're classifying points by taking the dot product with this parameter vector, and what that means is that implicitly our parameter vector is specifying the normal to our decision boundary. Now we're going to let gamma here, gamma I, be the distance from a training instance xi to the decision boundary. And again, our W is the normal to this. So if we're looking at this figure here, here we have our decision boundary. We have our point xi, and then this is the distance from xi to the nearest point on the decision boundary. So what we're interested in is we're interested in maximizing this margin. We're interested in doing some computation or doing some optimization on this gamma term. So we want to ideally have a model where gamma for all of our points is really big. In fact, for gamma that is the closest point to the decision boundary, we want to maximize that margin. Again, now we're measuring this gap, this no man's land, using this gamma variable here. But the things that we actually have in our data set, well, first off, we have our training data, so we have our xi's, the features for our training points, yi's, the labels for our training points, and we have our parameter vector w. These are the things we know, and w is the thing we have control over. And so what we want to do is we want to maximize, we want to set w so it maximizes this gamma. But again, we have to do this somehow with the three things we have and the one thing we have control over, which is just the parameter vector. So first off, what we can do is we can write down gamma in terms of these three things. So what we'll do is we'll take xi naught. We're going to let this be the point on the decision boundary that is nearest to the training point xi. So visually here we have xi, and then xi naught or xi0 is the closest point on the training boundary. And now the vector from xi naught to xi, or from xi to xi naught, is going to be the margin times the unit norm times our weight function, which is again going to be perpendicular to our decision boundary. So we're dividing this to get the unit vector that specifies the normal away from our decision boundary, and to get this line that goes from here to here, this is going to be the size of this vector, of this length, times the direction, which is given by our w vector. So again, w here is a scalar, and then this term, our parameter vector divided by the norm of our parameter vector, is the unit normal. So it's the thing that tells us the direction of our decision boundary. And then what we can do is we can then define that xi naught is going to be equal to this term here. It's going to be xi minus this. So again, if we're at xi, we know that this is the vector that goes from xi naught to xi. So the minus this takes us from xi to xi naught. A bit of boring algebra. But at the end of the day, what we can figure out, again, also by the fact that we know that this function xi naught is on the decision boundary. So taking xi naught dot product with our parameter vector must be 0. Again, because this thing is perpendicular, it's the normal to this plane. And also, this is by definition how we specified what w is going to be. So we know that w times xi naught, which is equal to this, has to be 0. That gives us this relation. We can then do some more algebra, and what we end up with is that solving for this gamma I term, if we're just looking at a positive example, gamma I is going to be w transpose times xi divided by the norm of w, and more generally, for any data point, the margin, the distance from that data point to the separating hyperplane is going to be equal to y times w transpose, so the dot product of w and x, divided by the norm of our parameter vector. So it's a bit of algebra, a little bit of linear algebra that maybe some of us haven't thought about in a while, but really at the end of the day, it's a pretty simple thing we want to look at. Is we're saying for all these different points, all we want to be able to do is get the distance from this point to this decision boundary, and we're assuming that we know w, and this w is by definition going to be perpendicular, or the normal, to this decision boundary, and from that we can figure everything out. So this tells us how to compute this gamma term, this distance for our data point to the decision boundary. But what we want to do is we want to maximize this. In particular, we want to maximize this margin. So what we want to do is that we want to say that this term, which is equal to gamma, so this is how far data point xi is from the decision boundary, this is going to be greater than mi, or greater than m, sorry, so this is going to be our margin for all of our points, and we want to maximize this margin. So let's find the biggest m such that all of our points are at least that far away from the decision boundary. And the thing, again, we're maximizing is m. And so we'll take a minute to let just digest, because this kind of way of writing down this optimization function, this optimization problem, is going to be what we're using for the next couple lectures. So we're always going to have this, what is the objective we're maximizing? What are the things that we're maximizing with respect to? And then what are the constraints? So the idea here is that what we're trying to maximize is our margin. We want that all of our points are at least this distance away from the decision boundary. So we're trying to maximize that term by fiddling around with our parameter vector. But we always need to satisfy these constraints. So this is an optimization problem. This is different from the learning problems we've seen previously in this course. We never had constraints before. We were trying to maximize or minimize some function, but we were never constrained. All we had to do was just take gradients and try to find the maximum or the minimum. But now we're actually doing constrained optimization. And what's unfortunate here is this isn't just constrained optimization, but this optimization problem here is actually, for one, it involves a nonlinear, so our w vector appears nonlinearly in the constraints, and the other issue is that this problem is under constrained. So the issue is that suppose we came to some optimal setting of our margin and our weights, so it's like, oh look, we've maximized this by satisfying these constraints. Well, we could always just multiply things by constants, and we still be satisfying this. So this is an issue when you're setting up these sorts of optimization problems, is that you can write them down and you think, okay, I can optimize this, and we'll talk about how you optimize these. In fact, for this, for the purposes of this course, there are solvers that optimize these things for you if you specify things correctly. But the important thing is you do have to specify things correctly, and this is what we call an under-constrained problem, because there's an infinite number of solutions to this. But we can get around that by adding a simple constraint. And what we do is we just add this constraint that the size of our parameter vector times the margin is equal to 1. And so what we get at the very end is that we're kind of flipping things around a little bit, and now what we're saying is that we're trying to find the minimum norm for our vector W such that all of our data points are at least distance 1 away from the decision boundary. So what we've done here, we just played a little trick by adding this constraint that makes it so that instead of having an infinite number of solutions, we have a single solution that is still satisfying what we want. We're still satisfying this where we're saying all of our points have to be a certain distance away from the decision boundary, and now we're trying to satisfy this thing. And then we don't stop there. We actually tweak things a little bit more. The first thing that we do is that this is the Euclidean norm, but as we know when we are looking at linear regression and other things, it's often nice to actually work with the square of the Euclidean norm. So that's what we were looking at when we looked at the mean squared error, for example. Yes? Yep. Maximize M. For the top one, should it be an inequality? No, I believe that is correct, because we want to have, so you're talking about right here? Yeah, so here we want this to be greater than the margin, and we're trying to make this as big as possible, but we only have control over this, I'm running out of batteries on my pointer, but this is correct. I'll double check afterwards, but this should be correct, because we're trying to say we want all of our data points to be at least a distance of M away from the decision boundary. So we're trying to make that M as big as possible. And it's a bit weird because we're maximizing M, but M isn't what we have control over. We only have control over W. That's the thing that's kind of weird. And then when we do it down here, we've actually gotten rid of M entirely, and now we're minimizing our parameter weights, the norm of our parameter weights, and trying to optimize these with these constraints. It's a little bit weird. It's a little bit different from, especially like the gradient descent algorithm we talked about previously. Yep. So, yeah, I think that is the right way to think about it, because in some sense, once we specify W here, this is going to tell us, in some sense, this is going to give us this side of this inequality. And what we're trying to do is we're trying to make this side of the inequality as big as we can. Yeah, but part of these confusions are actually part of why this first version of it is under-constrained and strange. Because again, once we come to say we have an optimal W and M, we can just multiply these by a constant factor and still have the same, still have an optimal point. So that's why we have to actually do things as it's written down here. And in fact, at the end of the day, what we do is we take the square of the norm of our parameter vector, and we also divide by half just to make the math work out nice. And this is actually the optimization problem we end up with. So why do we do this? Well, for one, we do this because when we take the square, it makes it a nice, easy to solve convex problem. And then taking the 1/2, again, just makes the math work out nice. And we can do this because this is a monotone transformation, and so it doesn't change the decision boundary, or it doesn't change the optimal point. All we're doing is, originally we were saying, give me the smallest parameter vector you can, so minimize the size, the norm of the parameter vector. Now we're saying minimize the square of the size of the parameter vector. Those are going to have the same minimum. So it doesn't matter we took the square, but it matters for our solvers, because the way that we actually solve this is using what's called a quadratic programming solver. There is a large number of off-the-shelf ways of doing this. This is not going to be covered in this course. And this is a place where, unfortunately, in an ideal world, we'd have time to go over all of the background and details for convex optimization and how we solve convex optimization problems. But for now, you're going to have to just take my word for it and the word of people who design these solvers, that if we write down problems where our objective function is quadratic in our inputs and our constraints are linear, this thing is easy to solve. That's all we need to believe, and this is true, and I give a reference to a really fantastic online book on convex optimization by Stephen Boyd. He's a professor at Stanford, and I highly recommend, if people are interested in that,
it's worthwhile looking into. If you're going to take 652, you're going to have to get into a lot more of the nitty-gritty details of these kinds of things, and there are also courses on convex optimization offered, for example, in math. But today, we're just going to presume that we can plug this into a nice off-the-shelf solver, and that'll work for us. And again, in contrast to everything we've been doing in this course so far, the big difference here is that we're doing constrained optimization. So previously, we were talking about finding the minimum of some loss functions. That was generally what we did. We specified a loss function for our classifier or for our predictor, and then we said, okay, let's find the parameter vectors that give the minimum for this loss function. Now things are a bit different. We're specifying some objective. Again, here our objective is to maximize the size of the margin, but there's constraints now. And this is important because these constraints can have a big impact. So here is a very trivial example, but it's worthwhile to look at. So suppose that we were trying to minimize the square of x. Now if we were unconstrained, obviously the minimum of this is just going to be where x equals 0. But if we add constraints saying that, say x has to be greater than or equal to -1, well then we end up with there being two possible things we can do. We can have x equals 1 over here, so I should say x equals 1, and -1 or 1, right? So now that we've added these constraints, we can't just find the extremum of these points by running gradient descent or by taking derivatives. We actually have to think a bit harder, and the best solution is not going to be where the derivative of x squared equals 0. So now I'm showing an example here where we've used this convex solver, we've plugged in those equations and obtained our solution. And here, this is a nice plane where it's actually maximizing the margin between these points, or between the decision boundary and these points. And it's nice because we have a unique solution, but the thing that we're, in some sense, unfortunately still missing is, well, why are these things called support vectors? And what are these support vectors? And in fact, what we're going to do is we're going to remember this dual idea from the perceptron. So in the perceptron algorithm, we said that we could learn this parameter vector. We can also represent that parameter vector in terms of our input points. There's two ways of looking at our solution. Now we're going to do the same thing, but with this support vector approach. So where we're using this maximum margin idea to learn the best solution, again, we're going to be able to represent the learned solution as some linear combination of our input data points. But now it's going to be a special set of data points that are called the support vectors. And that's why it's called a support vector machine. But to get there, we have to go through a little bit of boilerplate math. And this is, again, a place where it's the most optimization in some sense we're going to cover in these two lectures. And so this is a very high-level, somewhat conceptual introduction to what are called Lagrange multipliers. Again, you will get a lot more detailed introduction to this if you continue on in machine learning, for example, in Comp 652. So we're going to consider that we have an optimization problem, like the optimization problem we were looking at, where we're trying to minimize some function f subject to some constraints, where we have constraints from gi up to gk, and we want the function gi applied to our parameters to be less than 0. So this is just kind of a general, generic type of optimization problem. There's a large number of optimization problems that fall into this category. For example, the optimization that we did a few slides ago. We're minimizing some function of our weight vectors here, subject to some constraints, some inequality constraints. And again, this inequality could go the other way because we can multiply things by -1. So that's not a big deal. Now what we can do given this representation, so we call this representation of an optimization problem the primal representation of the optimization problem. And from this primal, we can define something called a Lagrangian. This Lagrangian is just kind of taking this optimization problem and rewriting it in kind of a unified objective. So instead of having this minimize f subject to these g constraints, these inequality constraints, we're going to say, okay, now we have a new Lagrangian function, which is just our f, the thing we're trying to minimize, plus the sum over all of our g, all of our inequality constraints. with some alpha i's, some weights on these inequality constraints. These weights are called the Lagrange multipliers. And why do we do this? Well, the first thing we can actually look at is if we represent, so this is the primal p here, what we can say is that if we actually maximize these alpha i's with respect to this Lagrangian, so what we're doing is we're taking, again, f, the thing we're trying to minimize, plus the sum over all of our inequality constraints times each one times its own Lagrange multiplier. If we maximize this function with respect to all these alpha i's, we actually get the following very neat and very important relationship, which is that if all the constraints are satisfied, then this PW equals maximizing over this of the Lagrangian here, this is going to be just equal to FW. Because if all of our constraints are satisfied, then all of the GI's are less than or equal to 0. And so the best thing we can do is setting alpha I to 0 for all of these. But if that's not true, if there's one GI that's greater than 0, well, we can set that alpha I to infinity, and we can make P of W as big as we want. So the thing is that this Lagrangian, this maximization problem here, gives us a certificate of whether or not our constraints can be satisfied. It says that if I can maximize this thing and get greater than f of w, if I can go all the way up to infinity, this means that all the constraints can't be satisfied. One of these GI is greater than 0, and because of that, I can just blow up its alpha I and go all the way up to infinity. But if all of these GI are 0 or less, well, if I'm trying to maximize this thing, then the best I can do is setting all the alpha i's to 0. So another consequence of this is that instead of computing the minimum of FW subject to our constraints, we can actually compute this min-max problem, where what we're saying is that minimize W after maximizing with respect to all of these constraints. So we maximize this, and then we can minimize W with respect to this. And again, if this thing is these constraints are unsatisfiable, we're going to end up with this infinity here. But the idea here is that this max over all these alpha i's, this thing is trying to it's going to penalize the thing if we're making any of the constraints unsatisfied, because then this max term can make it infinite. So this min term wants to prevent this infinity, so it's trying to satisfy all the constraints. So we have this kind of game between these two different parts of the optimization. This is just a different way of writing down that original optimization problem. We took this minimize FW subject to these constraints. We've converted that into this minimax game. And one of the reasons why we do this is that we can actually flip this. Instead of doing this minimax, we can do a max-min game where instead of maximizing LW with respect to the alpha i's first, we're going to minimize with respect to the W vector first. So again, why we want to do this is that these two problems are actually going to give us the same answer, but they're going to give us the answer in different ways. So again, the thing we're trying to solve at the end of the day is that we want to minimize this f. So f in our case is the square of the norm of our weight vector. That's what we're trying to minimize. We're trying to do that with respect to our with respect to our parameters w, and we're trying to satisfy all these constraints. And if we write this down, this Lagrangian, again, f in our case is this term here, so this is the thing we're trying to minimize. Now, we have a constraint for each of our different training points, so we sum over all of our training points, because each one we want to have be greater than 1 here. So we're summing over all of these, we're multiplying each of these by this alpha term, and this is the Lagrangian for our SVM, our linear SVM problem. And again, we can represent this as, instead of this optimization problem at the top, we can represent it as a minimax game or as a max-min game. And now getting a little bit into the nitty-gritties, so if f and g are convex, then what this means is that the optimal weight vector for the primal solution the optimal solution for the primal is going to be the same as the optimal solution for the dual. And the other important thing here is that when we're actually looking at solving this dual, what we can do is we take the derivative of this Lagrangian. So again, when we're solving the dual, here, and I apologize that I can't point anymore. So when we're trying to solve the dual, we're trying to solve this max and then this min problem. So first we're minimizing with respect to W, and then we're maximizing with respect to all these alpha I terms. So we can solve this kind of in two steps. So you can think about that solving the minimization now, it's unconstrained, so we can just do our standard taking derivatives and setting to 0. So if we take this Lagrangian, we take the derivative with respect to W, and we can figure out what are the optimal W, what's the optimal W for this Lagrangian. And this is what's going to give us the min part here. And now we solve for that W star, and now what we want to do is we're actually trying to do the maximization outside of that. So we can plug this back into the dual. And at the end, if you feed this math through, so we're taking that, again, the W here, the best W is going to be some linear combination of all of our input points. But what we're trying to do is we're actually trying to maximize this function for the dual, where we're trying to maximize over all these alphas. We're trying to maximize alpha I minus 1/2, and then there's a little bit of a mouthful of a term there, but it's just some nice linear terms. And at the end of the day, what we're going to end up with is that, supposing we've solved this entire thing, and I do apologize I can't point, makes this slide a little bit more difficult. What we're going to find at the end of the day is that once we've actually solved this problem, we have all of these alpha i's, and again, the important thing here is that our parameter vector W is just some linear combination of all of our input points, with that combination specified by these alpha I weights. And what we're going to end up with is that for a large number of our points, these alpha i's are just going to be 0. And in fact, the alpha i's are only going to be greater than 0 for points where we're right on the decision boundary. And this is important because this is basically saying that all we really need to look at when we're specifying our decision boundary is a set of points that specify that margin. Sorry, they're not right on the decision boundary, they're on the margin for the decision boundary. So these are points where 1 minus our decision boundary is equal to 0. So these are points that are directly on the margin. So after we've done our optimization, when we're looking at this dual optimization, where what we're optimizing over in this dual is that we're first getting the W and then we're maximizing these alpha i's. Well, if we do this, at the end of the day, what we're going to end up with is that the alpha i's are going to be 0 for all the points that aren't on the margin, that aren't actually contributing to our decision boundary, and only greater than 0 for points that are on the margin. And so we call these points the support vectors. This is where the term support vector machine comes from. And our decision boundary now is just going to be a sum over all of our data points, the alpha I for each of these data points, times yi and the dot product of the feature vector for that support vector and our input vector. So again, what we've done here is, in one hand, we've solved an optimization problem where we're trying to find the minimum W that satisfies this. And that's a reasonable thing to do. You can just solve this optimization problem using quadratic programming. But we went through all of this math in terms of specifying this Lagrangian, specifying this idea of the primal and the dual, and I glossed over a little bit of this here because it's just a bit of mathematical background that because things are convex, the primal and the dual are going to give us the same solution. So we can use either of these things. And once we've moved to this dual version, this tells us that this weight vector that we've learned is actually just a linear combination of some small set of our input points, which are called the support vectors. So instead of having to memorize W, what we need to memorize are what are the small set of support vectors and what are their weights. So we just need to memorize these alpha zeros, sorry, these alpha i's for the set of them that are non-zero. And why might you want to represent things in terms of these dual points instead of in terms of just the parameter vector w? Well, actually, sometimes that can save you in terms of computation, and we'll talk about in the next lecture actually cases where it's really important to use this dual formulation instead of the original formulation. So here, I do know that it seems like just a lot of somewhat abstract math without saying why do we actually want to represent these things in this dual form. Why didn't we just solve our original optimization problem that we had at the top there? The reason for this is that at the end of the day, being able to represent our decision boundary by a function of just our training points is actually going to be extremely useful. And it's going to be extremely useful because when we're trying to represent decision boundaries that are much more complicated than just linear, well, then we're going to have this problem that our w vector, or our function over w, can be much, much, much more complicated. And our decision boundary could be very complicated. In fact, in a way that I'll describe more concretely in the next lecture, we can have decision boundaries that require taking infinite expansions of our features. So instead of just looking at our features, we can actually care about infinite expansions of these feature points. So for example, taking these feature points and taking your features and raising them to a power of, say, power of 1 all the way to a power of infinity. So we can define all kinds of crazy expansions of our features. But by operating just within our support vector space, we can avoid actually computing an explicit model over these crazy expansions of our features. We can represent everything implicitly just in terms of our support vectors. So it's a little bit you have to take on faith at this point. Some things you have to take on faith is the fact that this dual optimization works, that we could take our original optimization problem, we could define this thing called the Lagrangian, that in fact our original optimization problem is equivalent to this min-max primal I've shown here, and that due to convexity this is actually again equivalent to this max-min dual, and that the solution for this max-min dual is actually going to correspond to just a number of these alpha i's where most of them are going to be 0. So a lot of this are things that fall out of the theories surrounding Lagrange multipliers and convex optimization. And just to make sure everybody is clear and happy here, I do know it's a bit of a heavy lecture, and you're not going to be responsible for being able to prove anything regarding Lagrange multipliers or why the facts in these 3-4-ish slides are true, but you are expected to be familiar with the outcomes here and at least have, taking a bit on faith, but believing that these things are true. And I highly recommend also taking some time to look at these min-max and max-min and convincing yourself why this min-max problem here is equivalent to this initial optimization problem. That's something that if you write it down, you stare at it for a bit, it'll become true. The fact that this is the same, this dual gives you the same answer, again, that's a bit more advanced, but something that you should be kind of comfortable believing at the very least. And so at the end of the day, what we learn is this hyperplane that separates our data points. This is just a linear plane W, but now we're not actually representing W vector as a vector anymore. We're representing it as just a linear combination of a small set of what are called support vectors. So this is, again, showing an example of one of these separating hyperplanes. And here, only these bold points, only these points that are lying right on the margin, these are the support vectors. So our entire model is just these 3 points along with the weights associated with these points. So we have 3 support vectors in this example being shown here. And we have some alpha i's associated with these 3 support vectors. And that is what's specifying our entire model. So what you should know for today is the perceptron algorithm. I think everybody was fully on board with that. This very simple approach to learning just by either subtracting or adding our input features to our weights. And then we went on to this idea of this margin, that we don't just want to have some separating hyperplane. What we want to have is the best separating hyperplane, the one that maximizes the margin. Then we talked about how to actually write this down in terms of a constrained optimization problem. And then we had a very quick, somewhat rushed foray into Lagrange multipliers and convex optimization. And at the end of the day, it's important to understand what are the primal and dual, why is the primal, this max-min representation, the same as our original constrained optimization. And at the end of the day, the solution we get is that we're representing our W vector as a linear combination of some small set of support vectors. So that's what's important to take away from for today. Next lecture, we're going to pick up on this. And again, we're going to talk about how to regularize, talk about how to actually do nonlinear versions of SVMs. Thanks. Whew, that's a rough lecture. Yeah.
About the last slide.
Yeah.
It's like since like the entire model in this case is defined by the data points on the boundaries of the margin.
Yeah.
So essentially we're only use like a fraction of the training example to train the model.
Yes. Well, but you have to use all of the data points to figure out which data
Yeah.
points to use.
So like does that mean like this like supporting vector machine is not really